Further Algebra, Lesson 4, Solving Problems Involving the Binomial Expansion. So far in previous lessons we've introduced the general binomial expansion for any n. We've also discussed validity conditions and how to deal with examples where the first part of the expansion is not 1. What we're going to do today is put all of this into practice and consolidate our understanding by looking at a series of more complex examples. So let's have a look at the first example. We have to find values a, b and c such that 2 over 2 minus x multiplied by 1 plus 3x is approximately equal to a plus bx plus cx squared. Now, a number of you will be tempted to start this by expanding the brackets in the denominator. Now, there may well be a way forward with that, but it's not the approach that we are going to take. Remember, in maths, there can be lots of different methods that lead to the same answer. So afterwards, if you want to try that and see where you can take that method, please do. But we are going to start with a slightly different technique. I am going to rewrite the left-hand side of this as 2 multiplied by, and then instead of 2 minus x in the denominator, I'm going to write that in the numerator as 2 minus x to the power of negative 1. And then again, instead of 1 plus 3x in the denominator, I'm going to write that in the numerator as 1 plus 3x to the power of negative 1. I can now carry out binomial expansions of 2 minus x to the negative 1 and 1 plus 3x to the negative 1. So I'm going to start with 1 plus 3x to the negative 1. It's the slightly easier one of the two expansions. As you can see, we have a 1 here at the start, which means we don't need to do any initial rearrangements. So we're going to need to make use of our binomial expansion formula, which is over here. And our n value, of course, is equal to negative 1 here. And in place of x, we have 3x, which we need to substitute into the expansion. So let's do this. We've got 1 plus n, which is negative 1 multiplied by our x term, which is 3x, plus n minus 1, which is negative 2, multiplied by 3x all squared, all over 2 factorial. Now, I'm going to stop here. Why is that? Think about what we're trying to do. We're trying to find a quadratic that is approximately equivalent to this result over here. Now, that means that I don't really need to produce terms which go beyond a power 2, particularly because we know that this expression here is equivalent to the product of these two expressions in yellow and green, and that means I don't need to go higher than a term in x squared, because when I multiply these terms together, I only want to keep terms going up to a value of x squared. So I'm going to stop here, and then I'm going to simplify this. So this gives me 1 minus 3x plus 9x squared, stopping, of course, at the quadratic term, the x squared term. So now let's expand 2 minus x to the power of negative 1. Now, this one, of course, doesn't start with a value of 1 at the beginning, so we need to do a little bit of factorisation first of all, as we've done previously. So a similar process, let's take the 2 out. Inside the bracket we then have 1 minus a half x there. And then expanding our brackets, we need to have 2 to the power of negative 1, and then we have 1 minus a half x to the power of negative 1. So, of course, 2 to the power of negative 1 is equal to a half, and what we need to do is now expand 1 minus a half x to the power of negative 1. I'm going to do this all on one line over here. So this time our n value is negative 1 and our x value is negative a half. Must make sure we substitute in negative a half x for x in the expansion here. So let's do our expansion. First term 1, and then we have plus n multiplied by our x term, which is negative a half x, plus n multiplied by n minus 1, which is negative 2, multiplied by x squared, all over 2 factorial. And again, I'm going to stop at the term in x squared, because remember, we only want an approximation that goes up to the x squared term. So we're now going to simplify all of this, making sure we multiply each term by the factor of a half at the start, and you will see that the answer we get is a half plus x over 4 plus x squared over 8. So let's gather the information that we have so far. We've rewritten 2 over 2 minus x 1 plus 3x as a product of 2 minus x to the negative 1 and 1 plus 3x to the negative 1. We've then used the binomial expansion to expand up to the term including x squared for both of 2 minus x to the negative 1 and 1 plus 3x to the negative 1. We're now going to take the product of these three. So I've got 2. Now for 2 minus x to the negative 1, I've got a half plus x over 4 plus x squared over 8. Remember, we're only going up to the term in x squared. And we're multiplying by 1, take away 3x plus 9x squared. Stopping there. So let's do this expansion. Now remember, we wanted to write the original expression as a plus bx plus cx squared, which means I can ignore any terms which are of a power of x higher than x squared. Okay, so let's have a look at how we're going to do the expansion. So for simplicity, I'm going to multiply the yellow part by the 2 first of all. So that then gives me 1 plus x over 2 plus x squared over 4, and then term by term I'm going to multiply by the green bracket here. So let's see what that gives us. So 1 multiplied by 1 gives me a 1. 1 multiplied by negative 3x gives me negative 3x. And then 1 multiplied by 9x squared gives me 9x squared. So far, so good. Now let's take the x squared over, the x over 2 multiplied by 1 gives me plus x over 2. Notice how I'm stacking the terms vertically, collecting like terms is a lot easier if we do it this way. And then x over 2 multiplied by negative 3x gives me negative 3x squared over 2. And I'm not going to bother multiplying the x over 2 by the 9x squared because that will give me a term in x cubed, and I don't need any terms in x cubed, so I'm going to ignore that. And then the last one, the only multiplication I have to do is x squared over 4 multiplied by 1, because any further multiplication will give me terms in x cubed and higher, which I don't need. I'm now going to simply add all these together to collect like terms, so adding vertically down, so that gives me 1 minus 5 over 2x plus 31 over 4x squared. So comparing with this result over here, we can very clearly say that a is equal to 1, b, which is the coefficient of x, is clearly equal to negative 5 over 2, and c, which is the coefficient of x squared, is clearly equal to 31 over 4. So the last thing we're going to do is have a look at the conditions of validity here. Now, because 2 expansions were involved, we need to consider both the sets of conditions of validity. So the expansion for 2 minus x to the negative 1 is valid for mod x less than 2, which means that x can lie between 2 and negative 2. And I'm going to illustrate that on this number line below. So that tells us that x can lie in this yellow region here. Now, the second expansion is valid for mod 3x less than 1, which of course is mod x less than a third, which means that x lies between negative a third and a third. And I'm going to illustrate that on here as well, which is about here. Now, how do we then choose the overall validity condition? We have to choose the stricter of the two inequalities, because the green expansion is only valid across x is a negative a third to a third. Now, the yellow expansion will be valid for this condition. It will be valid for other values of x, but because the green expansion is not valid outside this much smaller range, we can't go outside the stricter inequality. So overall, we always choose the stricter result. So the overall validity condition for this question and this expansion is x is between minus a third and a third. Example 2. So part 1, we need to find the first 3 terms of the binomial expansion of this result over here. So first thing we're going to do is rewrite this as 1 minus 2x to the power of negative a third. So we can see we have everything set up ready. We know that our n value is equal to negative a third. Now we're going to replace x with negative 2x from our expansion, and we very clearly have the 1 we need in the first position there. So we're absolutely good to go with our expansion. So we're only finding the first 3 terms, so we only need to go up to and including the term in x squared. Let's do this. So we have 1 plus nx, which is negative a third, multiplied by x, which is negative 2x, plus negative a third, which is n, multiplied by negative a third minus 1, n take away 1, multiplied by x squared, all over 2 factorial. And in theory plus dot dot dot, but we're going to stop there. So let's simplify our terms. So we have 1 plus 2 thirds x plus 8/9 x squared. Now, there is a second part to the question here. State the set of values of x for which the expansion is valid. So we can say that the expansion is valid for mod 2x less than 1, which if we simplify gives us mod x is less than a half, or if you prefer, written as an inequality without the modulus, like this. So continuing with this example, let's look at part 2. We then have to find values of a and b such that this result here can be approximated by these 3 terms here. So the result that we've been given is 1 minus 3x over the cube root of 1 take away 2x, which we are going to rewrite as 1 minus 3x multiplied by 1 minus 2x to the negative a third. And of course, we can then replace our 1 minus 2x to the negative third with these 3 terms that we have found from our expansion. 1 plus 2/3 x plus 8/9 x squared. And then we simply have to do an expansion, term by term, going up as far as the term in x squared. So let's do this. So first of all, term by term, we've got 1 multiplied by 1, which is 1, plus 2/3 x plus 8/9 x squared. Stop there. Negative 3x multiplied by 1, negative 3x. And negative 3x multiplied by 2/3 of x gives us negative 2x squared. And we can stop there because the next term, which would occur if we multiplied negative 3x by 8/9 x squared, would give us a term in x cubed, and we only want to go up as far as x squared. So let's now simplify this and add these terms together. This gives us 1 minus 7/3 of x minus 10/9 x squared. Now we should always make sure we compare and check that our answer makes sense. We were trying to get to something of this format over here, and hopefully everyone can see that we've got a equals negative 7/3 and b equals negative 10/9. Example 3. So we're given the binomial expansion 1 plus qx to the power of p, and we're told that the first three terms of this infinite series expansion are 1 minus x plus 2x squared. We now have to find the values of p and q, state the set of values of x for which the expansion is valid as well. So this is a really interesting question. We have a value of n, but it's equal to p. It's another unknown. We have got a value of x as a replacement, so we're going to replace x with qx. And we can check we've got the one that we need as our starting point. So all we have to do is take 1 plus qx and expand it to the power of p. So our first term is 1, our next term is n, which is p, multiplied by our x term, which of course is qx, and we need to do one further term because, as you can see, we're going up to the term including x squared and no further than that. So we want n multiplied by n minus 1, multiplied by our x replacement all squared, all divided by 2 factorial. So we're then going to try and simplify this a little bit. So that's 1 plus pqx plus a half p minus 1 q squared x squared. Now, we need to compare this to the result that we were given up here. So this must be equivalent to 1 minus x plus 2x squared. So you can see straight away that the ones compare very easily. But what else? So the coefficients of x must be the same, which tells us that pq has got to equal negative 1. What about the coefficients of x squared? Well, this tells us that 1/2 p multiplied by p minus 1 multiplied by q squared must equal 2. And we have a pair of simultaneous equations that we are going to need to solve in order to find the values of p and q. So here are our simultaneous equations. We're going to solve them by taking equation 1 and rearranging it so it gives us q equals negative 1 over p. I'm rearranging in this way because there's only one reference to q in the second equation, so it means that there's less working to be done. You could do it the other way and substitute in for p, but that will require a little bit more working. So we're going to substitute this into equation 2, which tells me I've got a half p minus 1 multiplied by q squared, which is negative 1 over p all squared, and this equals 2. Let's simplify this. I'm going to multiply both sides by 2, which will simplify the left-hand side a little bit. The right-hand side will, of course, become 4 as a result, and then squaring this bracket here gives me 1 over p squared, which will allow for cancellation here. So I end up with p minus 1 over p equals 4, which is actually a much simpler equation than the whole thing looked like to begin with. So p minus 1 is equal to 4p, and p is equal to negative 1/3. This then allows us to calculate the value of q, which is negative 1 over p, which gives us q equals 3. So our expansion was 1 plus qx to the power of p. Well, this can now be written as 1 plus 3x to the power of negative 1/3, and the expansion is going to be valid for mod 3x less than 1, which tells us mod x is less than 1/3. So, example 4. Find the first 3 terms in the binomial expansion of this result here in ascending powers of x, and then state the set of values of x for which the expansion is valid. So here we go. Now we're going to need to do 2 parts to this because, of course, 1 plus 2x over 1 minus 2x all squared can be written as 1 plus 2x, which is the numerator, multiplied by 1 minus 2x to the power of negative 2. So our first job is to expand 1 minus 2x to the power of negative 2. Now it's set up very nicely. We've got the 1 that we need over here. Our n value is negative 2, and our x value is negative 2x, effectively. So we have the expansion over there on the right-hand side. Let's find the first 3 terms of this. We don't need to go beyond that because at the end of this we only need 3 terms in the final answer. So we've got 1 plus n multiplied by x plus n minus 1 x squared over 2 factorial. And let's simplify that. So we've got 1 plus 4x plus 12x squared. So we know that 1 plus 2x over 1 minus 2x squared can be written as 1 plus 2x multiplied by these 3 terms here, 1 plus 4x plus 12x squared, approximately. So let's carry out the expansion. 1 multiplied by 1 is 1. 1 multiplied by 4x is 4x. 1 multiplied by 12x squared is 12x squared. Then let's add on the second part. So we have 2x and 8x squared. Let's add these together. Actually, I'll do this over here where there's a little bit more space. So we have 1 plus 6x plus 20x squared. Now state the set of values of x for which the expansion is valid. Well, we've only expanded 1 minus 2x to the power of negative 2. So our validity condition for this is simply mod 2x less than 1, mod x less than a half. There we have it. So example 5, last question here. find the first three terms in the binomial expansion of this result here, state the set of values of x for which the expansion is valid, and then we've got to follow up part 2 as well. So first job is, of course, to rewrite 1 over the square root of 1 minus 2x as 1 minus 2x to the power of negative a half. So our n value is negative a half. We're replacing x in the expansion with negative 2x, and we have a 1 at the beginning, so we are good to go with our expansion. So 1 plus n multiplied by x plus n minus 1 x squared all over 2 factorial, and then just make sure we simplify this very carefully. So we've got 1 plus x plus 3 over 2 x squared, and there we have our first three terms. Now, hence find the first three terms in the series expansion of this. We've now done multiple questions like this, so we simply have to rewrite this as 1 plus 2x multiplied by 1 minus 2x to the negative half, which we can say is approximately equivalent to 1 plus 2x multiplied by the result we've just found the first three terms of in our expansion. And let's do that. So we get 1 plus x plus 3 over 2x squared plus 2x plus 2x squared, and that's as far as we need to go. Simplifying this term by term, we get 1 plus 3x plus 7 over 2x squared. Now, one thing we haven't done, which we were supposed to do a little bit earlier, is to state the validity conditions of our expansion, and hopefully we can all see that the expansion is valid for mod 2x less than 1, i.e. mod x less than a half.